So I'm glad to present our work, and our work about, I would say, integrated solution of radical pilot, and that how we actually pronounce that one is a PMIx PRRTE. And this one integrated solution is focused on executing heterogeneous workloads at large scale on partitioned HPC resources. And this is very important about speaking heterogeneous workloads and about scaling that during the execution on HPC resources. And yeah, there it is. And here is the just outline of my talk, the motivation, background, experiment setup. That would be also like background and experiment setup will be a core part. And then as a result, we will see like what we actually got out of this integration. And what the motivation of our work is, it is about to have a task heterogeneity. And while we're having that task heterogeneity, it actually brings up complexity into management process, and specifically management process as for resources and also for execution. And one of solution for resolving that one is about like focusing on the resource partitioning and the distribution of the tasks execution over that partitions. So we do have scaling while using partitioning of the resources. And with this work, we actually did explore the different partitioning setup configurations. And that's actually helped us to find out some limits within the performance and layout of it. Short background about what these tools are. And the first one is actually, this is a PMIx PRRTE. And PMIx is the application programming interface standard. It actually helps to describe methods with which happening interaction with the system level process. And one of its implementation is this PMIx reference runtime environment. And this one actually environment, it includes such entity as a distributed virtual machine that actually handles tasks placement, executions, and it does communicate with the system level. And this Ddm, that's actually what we also will use during this presentation, as well as what we use within references to this partitioning. So to start the Ddm, there use the specific command, which actually run the daemon on nodes, and that helps these nodes that belongs to one Ddm to communicate. Another part of it is the radical cyber tools. That's something as I would call it as an ecosystem. So it does present abstraction-based suite, and it provides abstraction for management for applications to manage workflows and workloads. And here, just on the left bottom, this picture, you can see these different levels. We do have a radical saga that's actually interface that does communicate with the computing resources and specifically with the HPC platforms. Then on top of radical saga, there is such a component as a radical pilot. This is the pilot-based runtime system. It does manage workloads, and with the workload, what I mean is a bag of tasks that with no interdependency between all of them. So dependency is supposed to be resolved before to pack the task here. And a layer that is on top of radical pilot, that's actually a layer that is capable to manage workflows. And this layer, like radical NTK ensemble toolkit, is responsible to resolve these dependencies between tasks, and it does communicate with the pilot, and through the pilot submit the tasks for execution. And going next, and what the actual radical pilot here Radical pilot does communicate with the infrastructure, with the resources. It used the idea of the pilot job, and it does submit a pilot job as the placeholder. It sits in a queue, batch queue, and when it's actually submitted for execution, then the tasks pulled from our communication layer, which is here MongoDB. And so Radical Pilot has these two main components as the client side and the agent. And on the client side, tasks are submitted to the agent through the MongoDB, through this communication layer. Thus, when the pilot is actually start execution on a resource on a HPC platform, the tasks are pulled from MongoDB and the execution starts. And here is with the schematic, it's actually showed that on a login node, we do have such sub-components as the pilot manager and task manager that manage these entities. They do interact through the Radical Saga with the compute nodes, with the execution part. And here is on the bottom side of this picture, we do have sub-components that actually running on resources. This is the scheduler sub-component, executor. And going further, we do with this figure, with this picture, it actually showed the integration of RP and PMIx PRRTE, and how that integration is actually happening within the RP. We do have such a sub-component as a resource manager that does responsible for acquired resources and specifically compute nodes, and also it is responsible for management of services to support the execution process, to support the executor sub-component. So in the case of PRRTE, such services are responsible to launch DVMs, and as I mentioned earlier, it happens with the PRRTE command, and resource manager also responsible to split that all acquired resources among DVMs in case if there are more than one DVM. We did have our initial study when we had just one DVM, and it was like previous releases of PRRTE, and that one was a study about running homogeneous tasks and using just one DVM, and performance was made a performance evaluation of that compared to using not PRRTE but JSRun. So this is part about resource manager, and then we do have a launch method that is part of executor. So while DVMs are running and to submit and place tasks, we use this launch method that actually uses prrun command and communicate with the corresponding DVM. And in our case, we already use a certain implementation of PMIx client that is within this prrun command, and we don't use a specific method. So, which I mentioned here is a PMIx pound. So it's PMIx client is not directly integrated into RP, but rather we use already certain implementation to communicate with the DVM and PRRTE. And just for the record, because definitely everyone already knows about Summit, and this is the machine that we use for experiments. And so before when we used it was #1 in the ranking top 500. Now it is #4 since Frontier machine #1 at OCF was announced. Hopefully our next experiments also will be on a Frontier. And couple words about experiment setup and specifically design. So what actually we used for workloads to make experiments? There are several use cases that we considered before to create a synthetic workload to make these experiments. And based on that use cases, I mean, we considered that use cases to create our synthetic workload. And it was important to cover that significant heterogeneity characteristics from that workload. And specifically, I talk about like task size and duration. Based on that workflows, we tried to create this workload with the different type of tasks, different, that's also tasks would use a different amount of resources, different number of CPUs or GPUs, and of course with the different durations. Thus all that brings that heterogeneity into the workload. Also, while creating that workload, our goal was to fill out provided resources. We didn't try actually to fit exactly all available slots in a provided nodes, but we did it on average. We used the average characteristics per task type to bring some random aspect into this. And of course, it was important to set up correct tracing events to capture all that performance characteristics. And here's the description of workload that we've got. We came out with the 8K heterogeneous tasks per each 256 nodes, and the tasks were split into two groups. The majority of the tasks, it's really small tasks, up to nine CPU slots. On a summit, Summit allows to actually turn on such a feature as to use hardware threads on each core. Thus, we used all these hardware threads per core, and in total, it was 168 slots that actually was provided each compute node. And small tasks were really taking a small portion of it, but we also wanted to bring up large tasks in a way that it will take up to 2 tasks on average per node. Thus, you can see that like for large tasks, it is from 68 to 84 computing slots, the size of such large tasks. And some of these tasks from a large type, they also, for them also are assigned GPUs. Another feature of, another differences between these task types, their runtime. So for small tasks, their runtime is really like twice smaller than the large tasks. So overall, if we'll use 256 nodes and run this 8K tasks, then it will be two generations of large tasks. It's like within each generation, task could be executed concurrently. So the total number of large tasks could be split in 2, and the total number of small tasks would be split in 4. That's kind of some estimation of the time that could be spent on the actual execution of this workload is around like 40 minutes. That's actually, we will refer on it at the end. And the amount of resources that we use for experiments, we started with the 256 and we went up to half of the summit is 2048 nodes. And we follow the week scaling. Thus, number of tasks was changed from 8K tasks up to 65K tasks. And our metrics of interest that actually, our goal was find out how much overhead actually PMIx and PRRTE will bring up into the execution process. So we did check the startup and the termination times for Ddm. We also measured the task set time within Ddm PRRTE when we actually launched task for execution, when it was assigned for DVM and how much that task set time actually took within the DVM portal. And we made analysis also on a task concurrency and finally as the total resource utilization. And our first experiments were focusing on Ddm Startup and Termination. And while we used in total just like 256 nodes, we were changing the number of nodes per DVM. And in this table, you can see the second column. This is the number of nodes per DVM. At the first, we had just one DVM and there were 256 nodes, and we've got such numbers for startup and termination time for DVM. But while we were increasing number of DVMs, so DVMs per node were decreasing, we can see that it is something that expected that startup and termination times were decreasing. But of course, while having really small while having really small startup and termination times, we have the total overhead is pretty high for the largest number of DVMs we had for these 256 nodes. This is also the case that all DVMs were started sequentially, and that's something that was recommended, thus each DVM wouldn't interfere to each other. And this one also affected the resource utilization, and from 85%, it dropped up to 65%. But it showed, like as we can see, since each DVM managed less number of nodes, it is faster starting and terminating. With the next experiments, we were focusing on that task setup time, and we had these three experiments for 256 nodes, and for further experiments, we were increasing number of nodes. Also, we were increasing number of DVMs. Thus, we were splitting that our allocated resources for 512 nodes, we split it in two. Then for 1,000 nodes, we split it in 8. And for the final, our experiment for 2048, we split in 32. And while we had with the left figure, while we had relatively small number of nodes and relatively small number of tasks, we actually see this trend that task setup time was decreasing while we did increase number of DVMs. Something that what we would expect also for bigger number allocated nodes and number of tasks. And that actually was the case when we see from 500 to 1,000. But something else actually started affecting when we increased it up to 2K nodes. And we'll talk about this later as well. So this is something that we wanted to capture. And here we can see that task setup time for small runs is actually not that big, not that large task setup time, but for a larger number of allocated nodes, that was something significant. Even the average time per task for setup time was kind of low, but for some tasks it was significantly high, 250 seconds. So that's something unexpected. And here is just the plot to show the exact the task setup time per task. So on an axis X, this is the tasks that ordered by start execution time, and on an axis Y, you can see that's the actual task setup time. And for 500 nodes, that actually got pretty high. But when we increase number of nodes and also increase number of DVMs, And while we increase number of DVMs, each DVM actually handle less number of nodes. That peak also decreased significantly, and twice in this case. With the next, this plot actually shows resource utilization, and we can see here on the third one pair of plots. That's about that is about 2,000 nodes experiments, and here is something unexpected that was on a radical pilot side, not on a PRRTE PMIx side, which is PRRTE PMIx with the color pink, and here is mostly the orange, which says about radical pilot. This one wasn't. We didn't find out what actually that caused the issue, and there was assumption about shared file system that actually pointed out that while tasks were prepared on a resource side, that actually at some point took the most time. And another plot that we use for analysis and to try to see how many concurrently tasks were within DVM PRRTE handling phases. So this shows all these tasks are when they were placed already to DVM PRRTE, and there are 3 stages inside of it, were like a setup, running, and termination. And at some point for all of these 3 cases, that setup time, we never reached that. It was not higher than 5K tasks were concurrently in a stage setup. And this is the final table that we actually got out of the 6 experiments, 3 experiments with the 256 nodes and the other with the increasing number of nodes. And you can see here task total execution time, and this is something that we would expect. It's about 2,400 seconds for all tasks, but for a higher number of nodes, that time was increased, and this one was due to this long task setup time within DVMs. And yes, this on the right side, you can see this time with the mean, median, and the quartile 3. As a summary, with all these experiments, we actually were able to explore these capabilities and limitations of PMIx PRRTE. It does show pretty good with the larger tasks, but having that small tasks that actually they did stressed PMIx PRRTE. And that information that we actually achieved gave us some upper threshold about the limitations that we had with the PRRTE. And just it is also important to mention that with that release of PRRTE that we use for experiments, that's a result that we've got. But later, after also our work was submitted and there was release of new version of PRRTE, and we did some experiments, and they showed significantly better results. Just at the end here, I want to show that this experiment with the 500 nodes, it shows significantly better time for task setup, which is less than 1 second for all 16,000 tasks. It was the same setup, experiment setup, and significantly better results. And with the resource utilization here, you can see really small amount of pink that actually that would introduce PRRTE to the whole execution process. Thank you for your attention.
Thank you very much. Are there any questions? what I like about this paper is that it is focusing on this really large machine. So I'm just wondering, do you plan to publish some of these workloads or traces maybe it's in the GitHub repository. On page 10, you mentioned some GitHub at the bottom, but I don't know whether it also includes the traces or it's just, you know, some description.
For now, it is just that code for the workload and also analysis tools. But we'll upload also the traces themselves, because this one is not proprietary data, because this is what we produced, and this is just really synthetic workloads.
Okay.
It will be there. Yeah.
Yeah, that would be nice. At JSSPP, we like workload traces, even synthetic ones.